So, welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome Kieran Rogers to give the talk. I'm going to hand over now to Ryan to do the introduction.
Yeah, so it's a great pleasure. Welcome Kieran Rogers again, who's visiting us from Space Telescope, where he's an ESA research fellow. To give us some background, Kieran completed his bachelor's degree in 2017 at Dublin City University in Ireland, where he majored in both physics and astronomy. He then moved to the Netherlands in 2019 to complete his master's in astronomy and astrophysics at the University of Amsterdam. And then after this, he accepted a PhD position to work at Leiden University, where during his PhD, he worked on some of the first JWST observations of young stars and disks. And then he finished last September 2025. And since then, he's been at the European Space Agency as a ESA research fellow based at Space Telescope in Baltimore, where Kieran is leading a really fantastic NIRSpec JWST program studying proplyd disks in Orion. And I think that's what we'll be hearing about this morning. So take it away. Thanks.
Thank you. Okay, so sorry, this meeting recording notification is stuck in the middle of my screen. So
we don't see that on the screen, so that's...
No, but I can't even control my screen anymore because it's in the way.
We can take 30 seconds for it to get reset.
Either break out and click out and
Yeah, no, it won't even let me escape, actually. It's awesome. Okay.
There we go.
Fantastic.
Okay.
Yes. It's always a new challenge with doing a Zoom meeting. Okay. So thank you so much for the lovely intro, and thanks so much for inviting me to be here. I've been having a wonderful time at the university, and I found Charlottesville to be a very charming town. I've been really enjoying myself here. I picked up my my Virginia Cavaliers t-shirt in the merch store yesterday, actually. So no, it's been really nice. Beautiful campus as well. So I'm going to spend the next kind of 35 minutes talking about the question that you see on the screen, which is how do planet-forming disks interact and react and respond to the external environment? Specifically, the environmental factor that I'm going to be addressing is the external UV radiation field. So let's start with the basics. Let's look at a simple cartoon of a planet-forming disk. This is our simplified view, and before we even consider the external environment, there's already a ton of things going on internally in the disk. Things like accretion, jets from magnetically launched winds. There's in the inner disk just gas, and then in the outer disk where you have dust as well. This is where planets are forming, where we see substructures like gaps and spirals. There's an extremely dense amount of information just within the disk alone. And so I put all these arrows in the figure to attempt to kind of overwhelm you by like, okay, there's already a lot going on. And now I'm going to have to tell you that there's a whole other dimension that we have to take into account, which is things happening outside of the disk and how that, what the interplay is between those internal processes and the external processes. And so the external factor that I'm referring to is UV radiation. And the reason why this is important in the first place is because most disks in the galaxy form in high mass star forming regions. And so most disks are born near a high mass star and therefore are bathed in UV radiation. And I think that there is somewhat of a bias in observations of planet forming disks because we have studied in much more detail the more nearby star forming regions where there are no high mass stars. And don't get me wrong, basically every major revolution in our understanding of disks and planet formation comes from these nearby regions. So I'm not trying to downplay their importance and significance, but I do want to highlight that if you don't take into account that things change for the disks in high mass star forming regions, which is most disks in the galaxy, then you may not have a complete picture of star formation, planet formation, disk evolution. So I'm flying the flag for UV radiation today. So the story begins back in 1979. Optical images are taken in a number of narrowband filters, so targeting emission lines, of the trapezium cluster in the Orion Nebula. The trapezium cluster is what we call where the high mass stars are, these O stars and B stars. So they're the big black circles that you're seeing in the image. And then there's this arrow which is gesturing towards this kind of blob that they detected for the first time. And they referred to these things as nebular condensations. There was this overdensity, a significant overdensity by 2 or 3 orders of magnitude compared to the more diffuse gas surrounding them. But they didn't know what they were. They just knew there was something there all of a sudden. In 1987, there's a kind of follow-up observation done by a totally different set of researchers, but they look at these same blobs now with the VLA in 2 centimeters, and they're able to actually spatially resolve these blobs. And they realize that they're actually the size of solar systems. They're like 100 AU in size. And so this is the paper where for the first time they suggest these may actually be disks that are being evaporated. And this is some really impressive insight because just a few years later, the Hubble Space Telescope is launched and we get the most absolutely incredible optical images of these things. And if we take a zoom in, we can see in so much more detail now what they are, which is, well, what the hell are they? We still have no idea because they look really weird. These don't look like anything that we've really seen before. So what do we see? We see this kind of tadpole structure. There's a really bright head, which is facing the high mass stars. And then there's this elongated tail, which is pointing in the opposite direction. And they call these things proplyds. And I'm going to use this word many times over. And the reason why they're called proplyds is because they realized and confirmed with these images that they are, in fact, planet-forming disks being evaporated. I'm going to swap now to a JWST NIRCam image to highlight how they knew that it was a disk. Although I should just clarify that they could see the disks in these images. I just like the NIRCam image better. But these HST images were the first ever direct images of planet-forming disks. And so this is a really, there's 2 really significant discoveries going on here, but it also partly explains why we call these things proplyds. It's just a shortening of the word protoplanetary disk, which has become very confusing because now a proplyd refers to a disk that is being externally irradiated with this kind of cocoon thing around it, even though the word proplyd doesn't reference any of that really important stuff going on. But that's astronomy for you. We come up with terrible names and then we're stuck with them. We swap to the NIRCam image. You can just about see this structure is still there, but clearly the HST images do a better job of picking up that cocoon. Let's move away a little bit. I have this object picked out where you can really see this absolutely, I mean, incredible structure. The same overall shape, the head, which is bright and facing the O stars, the tail pointing away, and nestled in between, magically, is this disk, which you see. I mean, you see, it's like 10 pixels across. It's fantastic. Okay, and so that's how they knew that these things were planet-forming disks. So they ultimately were able to detect like 200 of these things in the Orion Nebula. And since then, there have been more detected in other star-forming regions, although by far the majority are found in the Orion Nebula. And they have this amazing variety of morphologies. There's still some key overall, things that put them together, but clearly there's also a lot of variety in how they look like. Okay, so what is actually going on? What is this cocoon? What is the process causing this? Let's try to understand the physics a little bit. So we go back to our cartoon now, knowing that it's a disk, knowing that UV radiation is important. And if we zoom in, the UV radiation is coming into the disk and it is heating the disk up. And the most important heating mechanism is by the UV radiation being absorbed by a PAH molecule. The PAH takes in the UV, it's very efficient at doing this, and it spits out an electron in the process. So this is called the photoelectric effect. And when that electron flies out and goes through the gas, it heats the gas up. The gas is mostly molecular hydrogen, and it attains so much energy that it actually is able to exceed the escape velocity of the star, and so it flies away. And so we trigger this thermally driven wind from the disk. This process is known as external photoevaporation. And I find the photoevaporation word a little confusing because it is heat ultimately that drives the wind. It's not like a radiation pressure. But this is the word that we use, external photoevaporation. And so a very robust and rigorous wind is triggered from the disk surface. And that is what actually forms this cocoon structure that we see around the disk. It's mostly molecular hydrogen. The exact shape of the cocoon comes down to the balance between the pressure in the wind and the outside environment, as well as the balance of whether it's far UV radiation and extreme UV radiation. And that's why you can see such a variety of different disk shapes, but there's still an overall, major characteristic. So in this wind, there's a very strong gradient. You go from mostly molecular material close to the disk, and as you get closer to the head of this cocoon, you're meeting more and more UV radiation. And so you begin to dissociate the molecular content. It becomes atomic. You get closer still to the head of the cocoon. Now you're really seeing the extreme UV ionizing radiation. And so you ionize the gas. And so you have this gradient from molecular to ionized gas. And this is, by definition, photodissociation region. It's a PDR. And that's what proplyds are. Proplyds are mini photodissociation regions. And understanding proplyds and the mass loss and the structure of the wind, you have to view it through the lens of a PDR, which is kind of a departure from typical, isolated disks, because you don't have this external UV to generate the PDR. After those HSC observations came out, the community was extremely excited about them. We were seeing disks for the first time, and we were seeing the effect of UV radiation on disks for the first time. And so there were a number of papers in the late 1990s that developed the first, really successful models to explain how the photoevaporation works, the structure of the wind, the velocity of the wind, the launching mechanism. And one of the key takeaways from these papers is that although you might think initially that the extreme UV photons would be the best at destroying the disk and at, triggering the mass loss, it turns out that most of the proplyds are really dominated by far UV radiation. So in this figure, if you start at the top, you're far away from the high mass stars. And as you work your way down, you get closer and closer and closer. And you can see that we begin in an extreme UV dominated regime, then we enter into a far UV, and then go back to EUV. So it's for me, definitely not like an obvious sequence of events, but it turns out that most of the proplyds are really dominated by the far UV. And it's because if you go too far away, the far UV flux has dropped that you can't heat the disk up enough anymore. So it's not hot enough to escape. EUV photons will ionize anything that it touches, and so you're still able to generate a very thin, tenuous ionized layer where material is leaving. The mass loss rates are lower, absolutely, but you still lose mass, and it's through the EUV photons. Then you enter the sweet spot where the far UV can heat the disk up enough. And then if you get too close, EUV is now so strong in flux that it once again dominates. And it serves to push the entire cocoon down to the disk surface. The ionization front is no longer nicely separated with these stratified layers. Instead, it's sitting right on the disk surface. And so we would expect then for the emission of these proplyds to differ quite a bit, going from far UV dominated to EUV dominated. An important term that we should define here is G0, which is just the strength of the far UV radiation field. There are multiple different normalizations. Typically, we use the halving field, which is just this number. It's a flux. Higher G0 means closer to the O star. Okay, I've now jumped a lot in time. And I have admittedly skipped over a lot of really beautiful and important work done on proplyds, including when ALMA came online, a lot of what it was able to tell us about disk masses. I am apologetically skipping over all of that stuff, even though it's great, because for me, the next kind of major milestone, and I would say like the second era of understanding proplyds, comes from this paper. This is what kickstarts the next era. So Stefano Facchini et al. 2016. What they realized is, what was realized before is that although the proplyds are really cool and really beautiful, once you go far away enough, the mass loss is basically turned off. You're too far away, you can't trigger the mass loss anymore. And so there's like more than 1,000 stars in Orion and only about 100 or 200 proplyds. And so they're not a predominant thing that you find all the time. And it's because the mass loss gets turned off once you're far away enough. What Fachini et al. Realized is that dust in the disk is evolving. Dust is what is extinguishing the UV. And beforehand, we were treating the dust as if it was ISM, like small dust grains. But when you are in a disk, you start to grow dust grains. And this dramatically changes how the UV is absorbed and scattered and extinguished in general. And what ends up happening is for much lower UV radiation fields, you can pierce through much deeper into the disk than we thought, because the dust grains are larger, they can't absorb it as efficiently, and so you can trigger substantial mass loss at much lower UV radiation fields. And this changes the paradigm from proplyds being a curious kind of exotic type of structure and mass loss being important if you're really, really close, to actually external photoevaporation being important for most disks. Most disks in clusters, most disks are forming clusters, so most disks full stop. And that's the significance of this paper, is it makes external photoevaporation relevant for disks in general. Okay, so how is the mass loss actually calculated? We already know how to do this back in the late 1990s, but I'm going to focus on the more recent works that have done this. So one way to determine the mass loss rates is using the ionization front radius. In other words, essentially how far away the ionization front is from the disk surface, because this tells you something about the balance of EUV and far UV, as well as the density of the wind. And so if you combine that with how far away you are from the O star and how much flux is coming from the O star, then you're able to work out what the mass loss rate is. And this was done quite recently by Marie-Lie Aru and collaborators using Mu's narrow field mode observations. So this is another unbelievably beautiful example of a proplyd where every structure is, very well resolved. The disk, the jet, the ionization front. And so they're able to measure the ionization front radius for, I think it was about a dozen proplyds. And they find that the mass loss rates are about 10 to the power of -6 solar masses a year. And so if a disk is about 10% of the stellar mass, then we are destroying these disks in thousands to hundreds of thousands of years. This is a dramatic change from the expected lifetime of an isolated disk, which is millions of years. And so the real implication that we're trying to get towards, I think kind of one of the holy grails of understanding external photoevaporation, is do you leave the disks with enough time to actually build their planets, especially giant planets, which are forming at larger radii, where the larger radii are more affected by external photoevaporation just because they're less gravitationally bound. So that's one of the big questions that we're working towards. I don't have the answer today, just to warn you guys. Relatively soon after these, well, in fact, even before the Muse observations that I just showed, we had JWST, which was launched, and the first observations of proplyds from JWST came from the PDRs for All early release science program. This was really targeting the Orion bar to understand that large scale PDR, but they included 2 proplyds that are in the bar, and so they got those spectra as well. And the results were really, really impressive. Here's the spectrum of the disk that I just showed, called D203506. This is just the NIRSpec spectrum. They also have Miri spectroscopy as well. The disk, the spectrum is very rich and dense in emission lines. Ice absorption is present, PAH emission. It's atomic, it's molecular. PDRs emit a lot in the infrared. That's where they emit most of their light, in fact. And so with access to these infrared lines with really, high signal to noise, high spatial resolution, high spectral resolution. It was possible to really start studying these proplyds as PDRs in a lot of detail. And so what the PDRs for all team did is they took those molecular hydrogen lines, which is the bulk of the wind for most proplyds, and they fit those line intensities with a PDR code, the Muon PDR code specifically. And they were able to get a pretty good fit. There's some disagreement for sure, but there's also things that could be improved with a lot of difficulty with the Muon PDR code. So in fact, this is an extremely impressive result. And it's the first time this has ever been done for a proplyd. And the power of this is that you are directly getting the properties of the gas. You're getting the density of the H2, the temperature of the H2. And so from that, you can get a mass loss rate because you know that it's moving at the speed of sound. And these mass loss rates are, once again, 10 to the power of -6 solar masses a year. So it's a great validation that this is working because the method using the ionization front radius, a totally independent method, gives you the same value. So this is working. One other result that I need to mention from the PDRs for all program, although strictly speaking, this is in the MIRI wavelength range, and I'm talking only about NIRSpec for the rest of this talk, but it's a very significant result, which is the detection for the first time ever of the methyl cation CH3+. This is a molecule that had been predicted to exist and was really required to exist. This is going back 40 years because you need a way to explain the abundances and variety of complex organic molecules that have been detected in space. You need something that will take simple atoms and click them together to make these more complex molecules. And their money was on this methyl cation CH3+. It acts as this perfect catalyst, very reactive molecule that can bridge the gap between simple and complex. The problem is that they just never detected it in 40 years until it was detected in this disk of a proplyd. And so not only is this molecule not being destroyed by the UV, it may actually require UV to be seen in the first place. It has since been detected in isolated disks where there is no significant external UV field. And so certainly you don't need external UV radiation, but it could be that the internal UV radiation from the central star is responsible for this line. So this is really motivating and kind of setting the stage for the potential of understanding disk chemistry with JWST for proplyds specifically, and really how chemistry in the disk is responding to UV radiation. And the real significance of this is that our own solar system is very likely to have formed in an Orion-like cluster. And so the insight that we get from Orion can be applied to our own solar system. So this really has deep significance for understanding, how the Earth formed and life on planets, everything like that.
Ask a quick question here.
Yeah.
Can you point to the specific feature corresponds to the molecules, or does Spitzer ever get a chance to see it? Or
So it's this entire band. So the observation is in blue and the model is in black, and so it's this entire band of emission lines. I guess the most prominent is this kind of broader large feature. And I think in another disk they observed, the 203504 paper written by Alan Scruter, they detected as well, but it's more so you see this larger feature in more detail, and then these weaker lines are less obvious. But it's this entire feature, and I think it hadn't been detected with any other telescope before. Likely, in terms of Spitzer, it would be a spectral resolution problem as well as sensitivity, actually. So.
yeah, the feature looks pretty prominent. Wonder if Spitzer is missed it because it didn't observe the right target, or it's just because it's not sensitive enough.
Yeah, to this I'm not sure actually. I'm not sure what the history. I don't know if you're a Spitzer.
Saturated with Orion as well. You can't really isolate the disks from the background.
Yes. Good point. Yeah. Okay, so that was kind of a history lesson of our observations of proplyds. And so we're going to do a little recap now, and there'll be a short exam afterwards, so pay attention. In the late 1970s, the first images of these condensations, these blobs were taken. It's in the 1980s that it's first supposed maybe these are evaporating disks, and then shortly after that, Hubble confirms that they are, and these are the first ever pictures of planet-forming disks. Then we have models that are able to successfully explain how the mass loss is being triggered. You have to view proplyds through the lens of the photo dissociation region. Then I shamefully skip over all the work done in the intervening years until 2016, including all the work Ryan has done. I'm so sorry. Proplyds and external photoevaporation become important again because it's realized that the mass loss can be high even if the UV is relatively low, and consistent with the average UV experienced by most disks. The PDRs for All program gives us the first JWST spectroscopy of proplyds, and this brings us to the program that I'm actually talking about today, which is MORPOP, the MSA Orion Proplyd program. And this is really born out of the work done in PDRs for All, and a lot of people on PDRs for All, including the PI of PDRs for All, Olivier Bernet's co-PI of the MORPOP program. It was a chance encounter at Space Telescope a couple of years ago where we sat down and more so Olivier realized that the MSA could be extremely useful for these objects. And I was working with the MSA already, so I think I was right place, right time kind of situation. So yeah, pretty lucky. I have to mention in the last notch in this timeline refers to another program, Disk Ori, which is being co-led by your very own Ryan Boyden, as well as Lance Gruter and Olivier Bernet. And so about 1 year after the MSA program was accepted, the MIRI counterpart was also accepted, kind of amazingly. So in the coming years, we're going to be connecting the NIRSpec to the MIRI observations. We have the entire wavelength range for significant sample of proplyds in Orion, which is really, it's amazing. Okay. This is the MORPOP team. It's an ever-growing list of people because the more we look at these spectra, the more we realize what we can do, and we need to bring in the expertise to help us do that. We're mostly based in Europe. I'm the only person based in the US right now, so I'm trying to fly the flag. So let's talk about what the program is, and specifically the MSA. So this is the micro shutter assembly on NIRSpec. It is a component of NIRSpec that enables multi-object spectroscopy. So the way it works is this. It's an array of 250,000 microscopic doors. You can open or close those doors in any kind of pattern that you want. So this is, you can imagine just a small section of the overall MSA. And you will open a micro shutter, you'll command it open, that corresponds to where your source is on the sky. We always open 3 micro shutters because we want to observe background spectra as well, which ultimately need to be subtracted. Now, these proplyds are big on the sky. So you can even see in this cartoon that the emission from the proplyd bleeds into the upper and lower shutters. So we don't actually have clean backgrounds in this case. And to get around this, the telescope is knotted. We move the telescope up and down. This reveals new background regions, ensuring that we have clean nebular spectra, which ultimately are used to do the subtraction. Of course, these nebular spectra are very rich as well. There's a lot that you can do with these spectra also. This is the distribution of sources on the sky. So I'm highlighting here Orion cluster. This is where the massive stars live. It's the 1 million pixels that are saturated here that you can't see with the NIRCam. In fact, almost every star in the cluster is saturated. Only like brown dwarfs and edge-on disks don't saturate. So that's the sensitivity of NIRCam for you. I also have here the Orion bar. And so we have sources kind of all over the central region of the Orion Nebula, some that are quite far away, some that are close. Here's a breakdown of the observations. We have 88 disks in total. Of that, 51 are known proplyds with these spatially resolved cocoons. We have 528 nebular spectra. We have an additional 129 spectra that sample things like the ionization fronts, and in many cases, the Kleiman Low Nebula or the Orion fingers. These are explosive outflows coming from a star-forming region located just behind the ONC. And if you ever look at the molecular hydrogen images of Orion, they stand out. They're one of the most magnificent things you'll ever see. It looks absolutely incredible. And at the very end of planning this, we had shutters left over, and we thought, oh, we'll open them over these. And the spectra are absolutely unbelievable, and they're adding on years of additional work, and they really came for free. And so I'm delighted. I focus now just on the proplyds though, but there's a ton of data coming from this program, which was a total requested time of just 5 hours. 1 hour of science time, 5 hours in total. The signal to noise ratio is about 40 on average for the proplyds. So these things are pretty bright. You don't need to look for that long. And so, yeah, this is a very efficient way of observing. The price you pay for that telescope efficiency is that then I have to reduce the data for like a year. So I do pay the price on that. It's worth it, or maybe I'm too far down the rabbit hole. I have Stockholm syndrome now. But you spend a lot of time reducing the data, but you're rewarded for it. You're very much rewarded for it. This is kind of the distribution of how we sample sources moving away from the O stars. So we go, in some cases, extremely close to the O star, very strongly irradiated objects, and then we move away to about 0.4 parsecs. This is close to where you kind of stop being able to see the proplyds very easily. So we made the sample to be biased on purpose. We wanted to see the cocoons. We wanted to get a lot of emission. But certainly you could do this again and do a more uniform sampling of objects to reduce that bias. But this is maybe something I should be mentioning, is that we've never had near infrared spectra of these objects before. This is the first time that we're getting this kind of spectroscopy. And so the fact that we're getting more than 50 of them in one go is it's wonderful. But I'm sure we'll do better in the future. Here's one of the first spectra then. Let's start enjoying the spectra. We're going to go into a lot more detail on the spectrum in a second, but for now, I wanted to highlight the nebular subtraction. What we're seeing in the kind of light blue on the bottom is the nebular spectrum. It's got this exceedingly weak continuum, but then very bright emission lines. And this is why the subtraction is so important, because if you want to isolate the proplyd emission, you need the subtraction to be reliable. And a lot of the flux from the lines of the proplyd are actually coming from the nebula, about 30% on average. This is a number that we've just worked out because we've just completed this subtraction process for all the sources. So it's a non-negligible amount of flux coming from the nebula. You can see just about that there's a blue spectrum behind the red spectrum. That's the proplyd before subtraction. And then after subtraction in red, the continuum is barely shifted, which makes sense because the continuum of the nebula is not very strong. But the emission lines have all come down by a significant amount. So you'll absolutely overestimate the emission if you don't do the subtraction carefully. Okay, so let's actually pan across this spectrum and take a look. I've included a very non-exhaustive list of detected lines, really just, I'll admit, the strong lines that I recognize by eye. This hasn't been a formal line detection process. This is something that Ilan Skruter, the PI of the MIRI program, he's taking care of this for us with a tool he's developed called Patatmol. So there'll be a much more robust and comprehensive line detection list in the upcoming paper. But for now, let's just enjoy, I think, and enjoy what we see. And maybe you'll notice things that I haven't noticed. So we have a lot of atomic emission from metal lines, from helium, from hydrogen, wonderful photospheric absorption features from the central star. We have really an array of molecular hydrogen lines. We have ice absorption, PAH emission in the 3.3 and 3.4 micron band. We have fainter molecular emission like CH+, not CH3+, just CH+. More ice absorption, the CO fundamental band. It's very faint in this spectrum, but it can be very strong in other spectra. So there's a real amazing variety of emission lines, absorption lines, ice features. No spectra really look the same. They really look, it's not like a characteristic proplyd spectra. That's one of my takeaways already of just looking at these things. There's also there's a great variety of emission lines and a great variety from one spectra to the other. So let's now pan across a bunch of different spectra. Again, not going into too much detail, just let your eyes see the differences that you see, but you'll be noticing things going from emission into absorption. You'll be noticing photospheric absorption lines appearing and disappearing, the SED shape changing. There's lots of things that make these proplyds look different, even if on the sky they look like little tadpoles. So let's have a little pan through. So yeah, we're seeing in some cases molecular absorption. We're seeing a strong photospheric absorption, atomic emission lines here, very few molecular emission lines, but then here really a denser forest of molecular emission. Weak continuum, strong continuum, weak PAHs, strong PAHs, booming, beautiful CO fundamental emission, ice absorption, in some cases very, very deep for the edge on disks, in other cases very, very faint. Yeah, there's just everything that you could possibly want is in these spectra. There's an amazing variety, and it's very overwhelming to know, like, how do we do this? Where do we even begin? So it's a great problem to have, don't get me wrong. I'm extremely happy how this has worked out. So I'm going to end with some of the first results that we have. And I should emphasize now that I mentioned the data reduction took a good part of a year, and I was finishing my PhD for a lot of that. So the results are beginning to come out now, but it's all really work in progress. And so, yeah, I don't have a huge amount of concrete results to show you, but the work that has been done, I'm happy to present for now. So Paul Amio, he's a PhD student in Toulouse, working with Alain and Olivier, and he has been looking at figuring out what the real UV radiation field is at the disk. Because usually what we have to do is get a projected value. You know how much UV comes from the O star, and you project that to where the disk is. So you get an upper limit, because the star might be further away than the 2D distance, and there might be some extinction going on between the O star and the disk. And so Paul is using an oxygen line at 1.3 micron, which is very sensitive to UV radiation. And he's able to determine the true value of G naught from this oxygen line. We haven't worked out all the kinks, because in some cases, the UV is actually stronger than the projected value, which is the upper limit. And so this isn't perfectly worked out, but things like disk inclination will certainly be playing a role in tweaking all of these points. But in general, this is working quite well, because clearly it's scaling more or less with projected value. So we're going in the right direction. And so this is a really important thing to know, because the actual value of G naught, well, we don't know it, generally speaking. We use the projected value. And this affects how we interpret the proplyds in many ways, in the mass loss that we expect, in the structure of the wind, yeah, in lots of ways. Raphael Mashaka is working with Thomas Howarth in Queen Mary's University in London. He is taking care of the H2 line analysis. So this is a similar approach that was used in the PDRs for All program, using the Mudon PDR code. We take those H2 line intensities, we fit them with a PDR model, and it returns the conditions of the gas. But the advancement that's been made from working with Raphael and Tom is that they coupled it with really an external photoevaporation code. So it takes in those physical parameters that you get from the PDR code, and it tells you things like the UV radiation field, the mass loss, and I think the most exciting things are it's giving you things like dust depletion in the gas and PAH depletion in the gas. And these are things that you fundamentally cannot access from the ionization front. You need the PDR information. And so getting the mass loss trace is great, and also opens the door for doing this for spatially unresolved objects, because you don't need to spatially separate an ionization front from a disk if you can just measure the H2 lines. But I think, yeah, really the most exciting aspect of this is giving an idea of how dust is being, how it's evolving in the disk and then going through the wind and the PAHs as well. So we saw PAHs are mostly responsible for the heating of the disk. So it tells you a lot about how the disk is responding to the UV radiation. Okay, so to summarize, again, the program and the sample from this program is extremely rich spectrally in emission lines. It's very high quality. It's a very diverse sample. I'm over the moon with how it's gone, considering I haven't done this before. I think a lot of luck was involved, and I feel very fortunate that things have worked out how they have. Some of the major goals of this program are, of course, mass loss rates, which will be coupled with accretion rates. The accretion rates for these proplyds has not been measured before. So this is my personal passion project. Accretion is my thing that I love to do. And so the major goal for me personally is to measure these accretion rates. And if we combine them with the mass loss rates, we get the disk lifetimes for, the whole sample. And actually, there's much more fundamental things you can do if you compare mass loss rates from photoevaporation with accretion rates, because it tells you something about angular momentum transport in the disk, which is something that we still don't really understand, how stuff accretes in the first place. As I mentioned a moment ago, dust evolution and PAH evolution will come from treating these things as PDRs. And then this very large category of disk chemistry. What chemical features are we going to find in these things that we haven't seen before? What are the implications for how chemistry is changing in the disk because of UV radiation? And ultimately, the implications for planet formation. What are they? Thank you so much for listening. Thanks for the invite. This was a lot of fun. So any questions, please feel free.
Great. Thank you very much, Kieran. So I'm going to let Ryan handle most of the questions here, since I can't actually speak too much where I am. But so Ryan, please just take the questions in the room there. And if I have a few, but I'll let you guys go first.
Okay, sounds good. Are there any questions in the room? Yeah.
Thank you for a really cool talk. So apologies if I missed this, but I guess I'm wondering, so for the subtraction of the nebula spectra, how do you, I guess, how are you predicting what the emission are to subtract, I guess?
Yeah. So glad you asked. Is this this is a problem that I worked on in my PhD for a different MSA program, a more distant cluster. And this was the #1 challenge of that program, was you measure nebulosity over here, but your star's over here, and it's not going to be the same. How do you account for that spatial variation? There's two different ways of doing it. One is you take slices across the source, sampling pure nebulosity, and you go over the target and you go back to pure nebulosity. And you can just see how it's varying. And you can interpolate over the source to get an idea of, has it risen dramatically or is it basically flat? That's one way of doing it. That works pretty well. An even better way of doing it is using a line that is purely nebular, that doesn't come from the star. This doesn't work great for proplyds because they have ionization fronts, which are basically nebular gas. But if you are trying to isolate nebular emission from just a disk, then you can use a purely nebular line, like a high ionization line, a helium line, for example. You need extreme UV photons to produce the line. You don't really get that from the star accretion jets. And so it's only coming from the nebula. And so you just keep subtracting till the line disappears from your star spectrum. And so we're going to be using a combination of these things to deal with the proplyds, to get rid of the nebular gas, and then ultimately to get rid of the ionization front, because we need to subtract that as well to get the accretion rate. But this is like filling my nightmares, this process. So this is going to be difficult, but that's the plan so far.
Thank you. Yeah. Daniel.
Thanks, Karen, for the great talk. So I was wondering, like when I think of Orion, I think of a lot of like young class 0, class 1 sources, and like some iconic features from there would be the jets and outflows. And so like I don't know about proplyds that much, but then like what happened to the jets and outflows here? It seems like you only see the cocoon, the disk, and that's it. Am I missing something here?
No, you do see the outflows. You're not necessarily seeing these like Herbig-Haro objects, like the really dramatic outflows, but the class 2 objects do have jets, and they can be seen. In fact, let me go back to way back, unfortunately, to the PDRs for all program. You can do it. But in fact, you can even see it here.
We saw it for a second. That's okay.
Yeah. You can in fact see the jet coming from this object here. Yeah. And so there's a number of proplyds where in the near cam imaging, you see the jet. Generally speaking, these are considered microjets. They're not extremely prominent, and you need the right filter to pick them up. A forbidden optic or forbidden emission line is best, but you can see it in the Passion Alpha images sometimes. And so this is just part of the confusing story of where the emission comes from. There's contributions from nebular gas, ionization front, accretion, jets, the star itself. And so we need to peel these layers back one by one and isolate. Well, I don't really care about mixing up accretion and jets because we always mix them up. Everything we know about accretion is accretion plus jets. You know, the emission is usually a mixture of the two. But certainly for separating the nebular gas and the ionization front, that needs to be done to isolate, inner disk emission, let's say. So the jets are certainly there. They're in the spectrum. We'll have to figure out exactly how to interpret them.
Kieran, can I ask a question? Can you highlight the difference between proplyds which are EUV irradiated and ones which are only FUV irradiated in the spectra? Is that very clear?
Yes.
In the do you have two classes of spectra that you can easily tell which is which?
I don't want to say with 100% confidence that we can, but I think we're seeing the differences. The example of the image I'm showing here is in fact a proplyd that is only receiving far UV. There's no EUV, and that's because it's within the Orion bar. So it's embedded in this molecular cloud that stops the EUV from reaching it where the far UV can. And these spectra are extremely rich in molecular emission. You see a very robust PDR being formed. If I go to the kind of range of spectra I was showing here, I think a good example of an object where you're seeing EUV and far UV together, but it's far UV dominated, is this example here, where you are seeing a wealth of molecular emission. I don't know if by eye you're picking it up, but a lot of those smaller emission lines that are within the taller emission lines, this is all molecular emission. Some of those really big emission lines are also molecular hydrogen. But basically, if you're seeing a wealth of molecular emission, then you must be seeing a more extended PDR with a larger emitting area. And so you know that far UV has to be important, because when you go to EUV, you push the ionization front down, you compress the stratified layers, and you're going to be mostly seeing the emission from the ionized gas. And so if we go to what I think, a caveat here, I think an example of that would be sorry, this is becoming a bit of a mess.
It's okay.
Yeah, here's a nice example. Here, we see, you know, a totally different looking spectrum where the density of lines is significantly lower. And I can tell you that all of these lines that you're seeing are atomic lines, either helium or hydrogen. The picture is complicated here by the CO emission, but we're seeing in the imaging that sometimes we're seeing molecular emission coming from the inner disk rather than the photo association region. And the other important thing to mention is that this particular source is extremely close to one of the closest objects to the O star. And so this fits in with the story of it being EUV dominated. The molecular hydrogen emission has vanished from the spectrum. So I think the defining characteristic is you swap from a rich molecular emission spectrum to a purely atomic emission spectrum.
Great, thank you. Yeah,
We have a question online from Nick Ballering.
Hey, Kieran. Can you guys hear me okay?
Yes.
All right. It's a really cool talk. I love to see it. I was curious about how much do you have information for these proplyds about the disk size and orientation? And is that something that you're factoring into the analysis? I'm specifically wondering if you have inclination distributions for your disks. I would expect the ice absorption to be mostly for the disks that are highly inclined. I'm just wondering if you have enough inclination information for maybe images with ALMA or NIRCam to see if that holds.
Yeah, thanks for the question, Nick. The answer is basically yes. We have information on the inclination from a mixture of sources. I mean, the HST images are great for this because you really see when the disks are close to edge on or face on because they can be in silhouette. There's a wealth of ALMA and SMA observations of these disks, which gives you also constraints. I've been chatting with Ryan, who knows much more about these observations than I do, on exactly which objects we have constraints for, and we've yet to finish that discussion, so I can't give you a complete answer right now. But certainly, using these longer wavelength observations and having these additional constraints, this was a primary motivator for picking this sample. We wanted to include proplyds where we had lots of observations at lots of wavelengths. So we're in the process of, let's say, collating all that data together, but we plan to have a project where we fit really an entire SED, where we place the NIRSpec spectrum in there, eventually the MIRI spectrum, but then we use the ALMA, SMA, and even the HST optical data points. So we're going to really try to use everything that we have.
All right, great. And it's one other thing I'd like to add. Does your spectral setup cover the iron 2 line at 1.64 microns? I can't quite see your x-axis here. I didn't know how many of those iron lines you detect. That would be maybe a really good way to isolate jets and constrain jet emissions from that iron 2 line if you cover it.
Yeah, we do cover it. It's relatively, well, from my from looking at the spectrum and sort of by eye noticing the line, it's not extremely strong, but certainly it is detected in plenty of spectra. Sometimes because of the placement of the detector gap, it does fall into the gap. It's at a wavelength that's quite susceptible to not being observed, but we have detected it in a number of spectra. But I can't say much more. I haven't looked in too much detail.
All right, great. Thank you so much.
Yeah, thanks.
I have a quick question that I'd like to ask. So the getting densities and mass loss rates from H2 lines with using this code, do you worry about non-LTE effects with that modeling approach? I'm curious about the systematics and using Meta1 to get those quantities. Do you worry about some certain aspects not being well understood and implemented in the model, or do you feel that it's pretty robust, the treatment?
So I'm going out on a limb now as
Yeah.
not an expert on the PDR code. I am literally
Yeah.
the tab is open on my computer of the paper, so I'm trying to learn as much as I can about it. But I can say something about how this code works because there's a reason why we're using this code and not some other PDR code, because it handles the excitation of hydrogen through UV pumping, which is non-LTE,
Yeah.
and collisions with the most detail of any PDR code. The shortcoming of Muon is that it can't do shocks. And so if shocks are contributing towards your H2 line emission, we're going to miss that.
Okay.
But UV radiation is very efficient at generating H2 lines. And so we strongly suspect and already have evidence to show that most of the H2 lines are dominated by the UV. And even if collisions are important, the Muon PDR code handles those collisions.
Okay.
So you can see that the fits are not perfect one-to-one mappings, but it's characterizing overall the H2 lines, and it's giving us the mass loss rates that we expect. So
and it's in like an average density. Is it kind of, are you spatially mapping out the density, or you just get kind of a bulk value?
I think I could be wrong on this, but I think it's getting the density of the dissociation front, where the H2 line emission's coming from.
Okay, gotcha. And then one other question I have quickly then, if anyone else. So the oxygen lines, I know in studies other folks have done, there could be inner disk kind of photoevaporation contaminating those lines, and could that be an explanation as to why like the UV fields are stronger than you expect because there's central stellar UV kind of driving things up? Or is that because there's not just theta or C, there's other OMB stars that are also contributing at a potentially significant level? Are you able to sort out those two, or is it still kind of in prep?
They're two great points, Ryan. Honestly, they're spot on. The internal component and that there's multiple high mass stars, and you can have a contribution from both. At this point of the analysis, well, I think Paul is even here. I don't know if he wants to comment on this.
Doesn't have to.
It's still a work in progress, and this is just the beginning of this analysis. But yeah, that would certainly help to explain why we have these overestimates of G naught.
Okay,
absolutely,
because it's a factor of what, at most 10 or 5 or 2.
The overestimates.
Yeah.
No, it can be orders of magnitude.
Like more than 10 in some cases. Yeah. Okay. Very interesting.
Yeah.
Cool.
So following up, I just had a thought, are there any lines that are better at absorbing Lyman alpha versus like FUV to try and like disentangle where that emission is coming from? I don't know.
I don't know either.
I'm not sure much.
Think about that this week. Yeah.
Think on that. I've never thought about that before. I'll need to think on it.
Now, before we ask any more room questions, is anyone else online? We see a hand from John Black. Feel free to welcome.
Right. Thanks. Perhaps I could respond to one of the last, pardon me, comments that there are some specific resonances with molecular hydrogen and Lyman alpha, vibrationally excited H2, which is well populated by the general UV fluorescence. And it's possible that some of the infrared decay products of that cascade might sense Lyman alpha. Even more, there are also resonances with Lyman beta. And going back to, since I'm mentioning resonance processes, about the oxygen lines, it's possible that there's some additional excitation of that 1.3 micron oxygen line as a result of resonance pumping with a very intense nebular far UV oxygen line, the very same, the line at 1039 angstrom. So there might be a resonance enhancement of the O1 if the nebular emission at that specific wavelength is greater than simply the continuum brightness from the star.
It's a great point. Thanks for bringing that up. Because this in fact is why the cocoons are bright along their entire edge and not just the head, because there's a diffuse UV field from the nebular gas. So this is a great point.
Can I ask a couple of follow-up points then? The PDR modeling includes some assumption about the dust in the PDR, and how sensitive is it to that?
Yeah, so it's using it's building from this work in the 2016 paper where they take into account dust evolution. Exact prescription I don't know from the top of my head, but they're assuming not an ISM like dust size distribution. And this is what leads to the higher mass loss rate. So the choice of dust size distribution is definitely very important. The other important detail is the PAH abundance, PAH being the most important heating mechanism. So these are definitely sensitive parameters that you can play with.
Because I think you're saying you only get significant FUV driven loss when you have certain either reduced dust or, but
the change in the dust is important for proplyds that are a bit more distant, because this is where it changes how the mass loss drops with distance. But for the proplyds in our sample, they're very close. So I'm not sure exactly what the implication is or how it balances out. But the major takeaway from the dust size distribution paper is that it's the very distant objects where the mass loss is still high. So it's not necessarily applying to our sample, but it's still a good insight.
Okay, great. And I see we have Ashish here.
Karan, great talk. I was wondering, do we have senses of how many disk-less stars there are, and how does disk fraction changes with the G naught? Because that can also tell us something independently about how long this disk survive and what are the mass loss rates.
Yeah, no, it's a great point. So this is finally I'm bringing up one of those ALMA papers. They measured the dust mass for a number of proplyds, a mixture of ALMA and SMA, in fact. And I find this figure really compelling because it shows how, as you are closer to Theta Ori 1c, the O star in Orion, you have lower dust masses and they get, more and more massive as you go further away. So we see that disks tend to be more massive the closer that the further away you are from the O star. But, usually these observations are all biased in that they're looking for proplyds. We're not trying to just look at all of the stars there. So, when you look at the trapezium cluster, you see a bunch of proplyds. You also see a bunch of stars that aren't proplyds. What are they doing? They should be just as irradiated. Why do they have a cocoon? Is it because their disk is already gone? Where they're at a more advanced stage of evolution. It could just be a projection effect, but yeah, we're not necessarily just looking for the boring point sources. We tend to go for the dramatic, proplyid-looking things. So it's a good point.
Thank you.
One final question I have, which 30 seconds to answer. So this CH3 plus is really interesting discovery. Do you need that kind of UV-driven organic chemistry to explain origin of more complex species? Is that critical to forming comms and maybe seeding the initial conditions of life, or do you think that other chemical pathways like the snowline driven chemistry can also do that? And maybe this just helps get a little more. I'm curious how critical that is,
So certainly when the paper was published with the detection of CH3+, I think the final line in the abstract is that, the UV is required to generate it. However, since that detection, they found it in those isolated disks.
Yeah.
And so now we're back into debating, well, what is the most important mechanism? Is it a gas phase or, on dust grains? And is the UV absolutely necessary? This is up for debate. And it's so far outside my area of expertise. I don't dare comment anymore.
Yeah. Okay.
No, right?
No. Sam says no.
I think we have one more question online here from Doja.
Hi, thank you so much for the presentation. It was really interesting. I wanted to ask more broad question. I was wondering, does this new data that you're seeing gives us a better template for the early solar system, actually? Like, do you have something about it, something to say about it?
About earlier, like, how do you mean earlier?
Like the solar system, our solar system.
Oh, sorry. No, absolutely. That is, I think, one of the most that's what makes these observations so compelling and applicable to it's what makes them relevant, I think, most
Yeah.
relevant, because we are accessing the environmental conditions that the solar system formed in. Now, these proplyds are maybe a bit more extreme because we selectively pick them to be very close to the O star. We don't know if our own solar system was so close, but the general information that you learn about disk chemistry, about mass loss, these things can be applied with, careful caveats in mind to the solar system. And so, no, I absolutely see that what we're doing here is, building the pathway to form the solar system, whether we may need to scale things down and make it a bit less extreme, but you can't think that a disk in Taurus represents the solar system. There's no UV. The UV has to be included in the picture. Maybe the UV doesn't matter in the end. Maybe that's the truth. That's fine. But you can't ignore the UV. You have to take it into account and figure out if it's important or not.
Thank you.
But I
Thanks.
recall, Kieran, that there's discussions about the edge of the solar system. If you smooth out the minimum mass solar nebula, and maybe this edge could be due to evaporation. Do you I don't know, do you measure outer disk edges and see if there's any link to evaporation in Orion?
So I didn't follow on what the solar system outer edge connection is.
Well, as I recall, if you just smooth out all the mass in the planets, it's some kind of power law, isn't it, as you go out in radius, but at some point it looks like it's truncated. And at least I recall discussion that maybe that edge could be due to evaporation.
Right. Yeah.
I think like around 30 AU or something.
Or by a flyby that can only be explained by a dense environment like a cluster. I think
Or
that's
I
kind of
flyby, but yeah.
Yeah.
Yeah, so the other kind of compelling piece of evidence for the solar system forming in a cluster is the presence of these radionuclides that have been found in meteorites. So you need UV radiation from a high mass star, or even a supernova, but either way, a high mass star. So this is another piece of very strong observational evidence that we had to be near a high mass star.
Great. Well, we're at the hour here, so I think we should probably wrap up. But I guess you guys can thank Kieran there in person. But that was a great talk and discussion, Kieran. Thank you very much.
Yes.